For thousands of years, ships have allowed man to travel the globe, crossing the vast emptiness of the oceans. The rewards for these journeys have been huge. So is the cost when things go wrong.
It's incredible to see what happened. People are drowning in the ice-cold water.
But every disaster has radically changed the design of the ships that followed.
Every single decade, we learn more and more after every casualty.
Designers strive to make their ships stronger and safer by learning from the tough lessons of the past. From classic cruise ships to cutting-edge designs, modern vessels are literally built from disaster. Disaster at sea can be a terrifying and deadly experience. Often miles from assistance of any kind, passengers and crew have only themselves and their ship to rely on. The ocean is an unforgiving environment where there are no second chances. In 1994, 852 people died after the car ferry Estonia sank in the Baltic Sea. In 1990, a fire on board the Scandinavian Star killed 158 passengers and crew. And most famously in 1912, over 1,500 people perished in the icy wastes of the North Atlantic after the Titanic hit an iceberg. These and other tragedies highlight three of the primary risks faced by passenger vessels: collision, capsize, and fire. The designers of all modern passenger ships use every tool at their disposal to limit the risk of these dangers. And this can be seen clearly in Italy, where one of the most high-tech cruise ships ever built is nearing completion. This is Ruby Princess. $500 million, 290 meters long, and over 116,000 gross tons. Built to cruise the Caribbean, it's taken just 14 months to get the ship to this stage. Giorgio Gomiero is the man responsible for this cutting-edge project.
We are going something like 45 meters, 15 decks when we come at the top. Let's go. Ciao, buongiorno. Ciao. Okay, we are on board Ruby Princess. This is our latest ship that we are going to deliver in a few months.
With cabins for 4,800 passengers and crew over 19 decks, this ship will be a complete floating city, with every conceivable passenger facility built in. There are 5 swimming pools, 7 restaurants, and even a wedding chapel.
Watch your step. This is a bar, and it is a covered area. We have an hamburger bar, we have another bar over there.
Incorporated into this vast vessel are the latest advances in ship construction and safety systems.
When you start with a project, you have also to take in mind all the safety of the ship. And you have to build the ship also taking all these constraints. And you have to respect all these constraints till the beginning.
The process starts with 19,000 tons of high-quality steel plate. This is made into precise shapes by a plasma cutter, and then welded to form sections which piece together to make up the ship.
So we build the ship like a Lego, actually. The ship is built in the dry dock. We have these big sections that are taken in dry dock, they are put together. One big section is going on board. All the sections should go on like this, and the section is then welded and outfitted.
This huge structure is an incredible feat of maritime engineering, built to withstand the awesome power of the sea. Modern passenger shipping is now one of the safest forms of transport on Earth. But it wasn't always that way. April the 7th, 1990. The passenger ferry Scandinavian Star was travelling between Norway and Denmark, with 482 people on board. In the early hours of the morning, a fire broke out in an unused accommodation area. The fire gained strength and rapidly spread throughout the ship, producing clouds of thick, toxic smoke in the corridors. Desperate for oxygen, the passengers searched for ways out.
I heard this noise from the fire, and I saw all the smoke coming out from every open door. I remember that it was so much smoke, and it was like a very huge waterfall of smoke. Then I understood that this is a great disaster. This is terrible. People are dying here now.
At 3:20 a.m., with the fire out of control, the captain gave the order to abandon ship. Many passengers were still trapped inside their cabins. 3.5 hours after a blaze broke out on the ferry Scandinavian Star, rescue helicopters reached the vessel. Firefighters were confronted with a horrifying scene. 158 people were found dead. Trapped in cabins and corridors, many of them hadn't even made it outside to the deck. After evacuating the survivors, the smouldering ship was towed to Sweden, where it took firefighters a further 2 days to extinguish the blaze. The fire was later thought to be caused by arson, but however it started, the results were catastrophic. The ship had serious shortcomings that contributed to the disaster. No smoke detectors or sprinklers in the passenger quarters, malfunctioning fire doors, inaudible fire alarms. But these factors alone did not explain why so many died. During the subsequent investigation, 2 shocking discoveries were made. The first was that many passengers simply could not find their way to the emergency exits. The second was that the fire spread incredibly quickly.
Development of the fire came as more or less as a surprise to our investigators. The fire was much more intense and rapidly intense than we expected.
The investigation found a number of causes for the rapid spread of the fire. One was that large parts of the ship's interior had been coated with a highly flammable plastic laminate. But this plastic didn't just intensify and spread the fire, it also gave off highly toxic fumes.
Hydrogen cyanide is a very toxic gas, very dangerous gas, and this is a gas that with low concentrations also could kill people within a few minutes or even a minute. And it's actually the same gas as Hitler used during the war, killing the Jews in the gas chambers.
The hydrogen cyanide given off by the plastic laminate was the direct cause of many of the deaths. This could not be allowed to happen again. All passenger ships built today must adhere to strict rules regarding the type of materials used in their construction. Virtually all the material must be non-flammable and non-toxic. Antonio Bartolini is in charge of fitting out the passenger areas on Ruby Princess.
This is the main theater of the ship, which provides seating for over 800 people. This wall looks like wood. It's actually not wood, but is a thin veneer applied on a not flammable material. Also, the carpet is not flammable, and is made in a way that the smoke is not toxic.
Flammable plastic laminates like those used on the Scandinavian Star have been outlawed for use on passenger ships. But another reason for the rapid spread of the fire was more complex, and it concerned information.
Knowledge is everything, and information is critical in an emergency.
The accommodation areas weren't fitted with automatic smoke detectors connected to the bridge, so the crew didn't know that the fire had started on deck 3. So not all of the fire doors in that area were closed, and the fire quickly spread around the ship. The tragedy on the Scandinavian Star would become the catalyst for a new generation of high-tech safety monitoring systems. These are now mandatory on passenger ships, and the one being fitted on board Ruby Princess is state-of-the-art.
All these cables are coming through from all the detection systems on board and they are passing into the safety management system. These systems makes the operator to be able to monitor the ship for fire detection system, water mist heads, and fire doors, watertight doors, so you can always monitor your ship.
Using 2,500 kilometres of wiring, the safety management system has sensors in every area of the ship, so it can provide an instant snapshot of an unfolding emergency.
It's sort of remote eyes and ears of the operator. So it's sort of like having a big brother looking over you all the time, all over the ship.
This is one of the benefits of our age. We have technology. We know not just that one fire detector is going off, that multiple fire detectors are going off. Why is that important? It tells the officer on the bridge this smoke is progressing. This is not a detector failure. Something's going on down there and you need to take action.
Sensors are constantly vigilant, checking for smoke, temperature changes and flooding. Before Ruby Princess is handed over to the owners, 6,000 smoke detectors and heat sensors across the whole ship must be tested, a 6-month job.
So now he will activate the smoke detector and we will verify the actual alarm. Spray warning, no? Prima. The alarm has been activated and you see this was the peak of the smoke detection.
If nothing was done about this alarm, the safety management system would take over. Fire dampers would shut, cutting off the air supply to the fire.
Fans have gone from the red color to green color, so from running condition to the stopped condition. We've just stopped the air supply to that part of the ship.
The water mist system would then activate. This is the latest in sprinklers. Pressurized to 150 bar, the water is sprayed as tiny droplets.
It's a matter of minutes extinguishing fire.
Conventional sprinklers are problematic on ships as they allow large amounts of water to collect, which could cause destabilization or even sinking. The advantage of the water mist system is that it can extinguish a fire using very little water. And it's now widely used on many types of ship. The appalling events on the Scandinavian Star had far-reaching effects on the regulations regarding materials and monitoring systems. But the inquiry also revealed a much more fundamental problem with the ship. The evacuation routes were poorly thought out and managed. Many dead ends and twists and turns trapped disoriented people in the thick smoke.
We could see a lot of people dying just aside a fire exit. I think 12 people were found in a corridor with a dead end. And if you go back 1.5 meters from the dead end, there was a fire exit just to the outside, to the open, to the deck. And 12 people were found on the floor, dead.
In response to disasters like the Scandinavian Star, evacuation planning is now considered at the earliest stages of a ship's design. On Ruby Princess and other cruise ships, one of the primary aims is to make sure there's always a way out.
You have to avoid the dead end. Nowadays, all the corridor is designed in such a way that you can always find a different means of escape. That is the modern way to design the escape route of passenger vessels.
During an evacuation, time is critical. To ensure that passengers can escape fast enough, the evacuation routes are tested with computer modelling.
All the lifeboats are simulated by these areas here. You can see all people moving from the public spaces into the assigned area that correspond to the lifeboats. On this ship, we can demonstrate that all the occupants can safely be inside the lifeboats in approximately 20 minutes, so having a large margin in comparison with the rules.
The journey towards safer shipping has been a long one, and the disaster which advanced it more than any other is perhaps the most famous shipping tragedy of all time, the sinking of the Titanic. On the 14th of April 1912, with over 2,200 people on board, the Titanic was on its maiden voyage across the Atlantic to New York. She was the biggest passenger steamship of the day. In fact, the largest moving object ever created by mankind. Incredible luxury, combined with great speed, Titanic incorporated two major safety factors in her design. The first was a double-bottom hull, which protects a ship if it hits an underwater obstruction. The second were her compartments, which subdivide the interior of a ship to stop the spread of flooding. These and other design features gave the ship a reputation for safety and inspired great confidence in her passengers and crew. Some even called her unsinkable. But that night, they were proven wrong. Just after 11:40 p.m., the gigantic ship struck an iceberg. She was at least 560 kilometers from the nearest land. As the iceberg scraped down the starboard side of the ship, it caused massive damage.
This damage went for over 90 meters, and it opened up a third of its length of the starboard side.
The ship could have been protected by her double-bottom hull, but the iceberg had damaged the sides of the ship, above the level of the double bottom. As a result, vast amounts of icy water flooded into Titanic. In this situation, her other design feature, compartments, should have limited the amount of water that could enter the ship. But there was a problem. The damage had compromised not one, but 5 of Titanic's compartments, an impossible breach which would sink any vessel. What became critical now was whether she would stay afloat long enough for a rescue vessel to reach the scene. One aspect of the ship's design proved disastrous. As the damaged and flooding bows sank lower into the sea, the rising water reached the top of the bulkheads that formed the compartments, but these weren't completely sealed to the deck above.
The compartments themselves were not fully watertight. They were open at the top. So what happens is, as water goes into one compartment, it weighs down the ship, and if the ship goes down far enough, water will start to pour in to the next compartment. Because it breached 5 compartments, this cascading effect of flooding could not be stopped on the Titanic, and it went down in 2.5 hours.
When the steamship Carpathia eventually arrived at the scene, the Titanic had already gone down, and the majority of her passengers were dead. Over 1,500 people died in the disaster. Many factors are thought to have contributed. The quality of the rivets used in her hull, her high speed in a known iceberg area. And shipbuilders have learnt many lessons from this legendary shipping tragedy. One of Titanic's design features, the double-bottom hull, is still in use. It's still one of the best ways of protecting a ship from damage caused by a collision with an underwater obstruction, and has saved numerous ships from sinking. The reserve inner hull prevents water flooding into the ship. On Ruby Princess, this double bottom is 1.8 meters deep. To get a proper look at the hull, the ship would have to be lifted out of the water and literally cut in half. But just a few hundred meters away from Ruby Princess, there's a new cruise ship at a much earlier stage of her construction.
You can see here actually a complete section of the ship, and you can see how the ship is built.
This gives unprecedented access to view the double bottom.
The first level is the level of the double bottom. The double bottom is 1.8 meters from the keel and is there in order to give a safety in case of grounding of the ship. On board the passenger ships is actually specified to have a continuous double bottom from forward to aft.
Underneath, the scale and strength of this vast vessel becomes apparent.
Pay attention because there are a lot of workers. This is the shipyard.
The level of the double bottom is marked on the outside of the ship.
That sign, the T, the sign T, indicates the placement of the double bottom, okay? The double bottom in this case is more or less 2 meters.
Like the double-bottom hull, Titanic's other design feature, compartments, are also still used on modern ships, but with several important changes. One of the biggest improvements was to make the compartments absolutely watertight. This is the Fram. Right now, this brand new cruise ship is sailing near Greenland. But this ship isn't trying to avoid icebergs like Titanic. She's actively looking for them. Her passengers want to see these huge ice mountains close up. The Fram has been designed specifically for this type of cruising. Areas of the hull at risk of collision damage have extra thick plating, and the stem at the front of the ship is made out of an immensely strong single piece of steel. But it's her watertight compartments that are the biggest safety factor.
Outside here is seawater. My head now is about 2 or 2.5 meters below water level.
The bulkheads forming the compartments are welded on all sides to the decks and other bulkheads around them, making them completely watertight.
This wall here is a watertight bulkhead. The bulkhead is attached to the deck above. It starts in the bottom of the ship and goes all the way up to deck 3. No water can penetrate through this bulkhead.
Anywhere that pipes or wires pass through the bulkheads, there are rubber seals.
We have bulkhead penetrations that are waterproof. The pipes are sealed into these penetrations. There's rubber, and it's tightened together, so it's impossible for water to penetrate. I guess it's kind of nice if you don't want the ship to sink.
Another lesson learned about compartments after Titanic was that the more compartments a ship has, the less likely it is to sink after a collision.
Today, passenger ships are very highly subdivided, so simply having damage along the side of the ship doesn't mean a whole compartment running the entire width of the ship is going to flood. That flooding may not make it that far because the compartment is so subdivided.
Here on Ruby Princess, there are 19 compartments compared to Titanic's 16. Most of the bulkheads that form them have doors to allow people to move around inside the ship. These doors must be watertight and on Ruby Princess can be closed remotely or locally.
If a compartment is flooding, this sensor will detect the flooding, the eye level on the bilge, and you will get an alarm in the alarm log. And if they cannot stop the flooding, they will communicate to shut down the compartment, close the watertight doors, and permit the compartment to flood safely.
The lessons learned from Titanic are incorporated into virtually every modern ship afloat. But there was one aspect of the disaster that had a bigger effect on safety at sea than any other. It seems unbelievable, but on Titanic, there were only enough lifeboats for just over half those on board.
Because of the Titanic, today there is 100% capacity for all people on board in lifeboats.
For ships like the Fram that operate in remote areas, access to lifeboats is of paramount importance.
We are ready to release lifeboat number 4.
Lower lifeboat number 4 when you're ready.
Okay, you can release. When we are a long way from the coastline and also a long way from other ships, it's of course important to have the equipment that will ensure us to survive as long time as possible. So to have covered lifeboats with food and equipment that you need to survive for a long time, that is absolutely important for us. 150 people can fit in this lifeboat. It seems incredible, but you sit very, very close to each other. And that can also be a plus because of the temperature. Today is just a drill. Of course, we hope that we never have to do this in a real emergency situation. The lifeboat is more than good enough to spend time in, but we like it better when we can spend it on fun.
For the passengers of Titanic that did make it to the lifeboats, the ordeal was far from over. They had few provisions and minimal shelter. Many of them died of exposure because the boats were open to the freezing weather. Many lifeboats today are enclosed to keep the occupants out of the wind and spray and have advanced features to aid survival.
In this locker we have fresh water for the one who's in here in the case of an emergency. And there's half a liter for every person every day, 3 days. Inside this locker is a maintenance sheet for the engine. We have drift anchors. We have also food in these boxes. And we have thermal protecting suit, keeps us warm. This boat is basically a life support system in case of emergency.
Lifeboat provision on modern passenger vessels means abandoning ship is a far more survivable operation, and this is directly because of Titanic. But sometimes it's impossible to take to the lifeboats. This is often the case in perhaps the most terrifying type of all shipping disasters. Capsize. September 1994. The roll-on, roll-off car ferry Estonia was on passage in the Baltic Sea. There were 989 people on board. In the early hours of the morning, halfway between Tallinn and Stockholm, the ship encountered extremely heavy weather. Huge breaking waves relentlessly pounded the vessel. The continual slamming of these vast walls of water weakened the assembly of the bow visor used to load and unload cars. Just after 1 a.m., the hinges failed completely, and the visor was torn off. This exposed the open car deck behind and allowed water to enter the vessel. The effects were catastrophic.
Estonia, what's going on? Can you reply?
My immediate reaction was to try and find a way out, or find a life raft, find a life jacket. I could see the water coming onto the ship. I couldn't see a way of getting off, and I could see my life ending at that point, trapped inside the ship.
The ship capsized soon after. And at 1:50, the Estonia disappeared from radar screens. The ship had sunk to the bottom of the Baltic Sea. Helicopters and nearby ships arrived to help those that had made it to the life rafts. Only 137 people were saved. 852 died. The investigation into the disaster had a profound effect on the design and operation of car ferries and concentrated on two areas: bow visor arrangements and stability. In the past, stability had always been a problem on car ferries. This is because they have large open car decks, effectively one huge compartment stretching the length and breadth of the vessel. If water somehow got onto this deck and moved around freely, the ship could be destabilized. The phenomenon is called free surface effect, and it works like this. As the ship naturally rolls to one side, the surface of the water will stay level. This means that the water gathers on the low side of the vessel. The result is that the ship's center of gravity is raised, which has a destabilizing effect, sometimes to the point of capsize. The sinking of the Estonia wasn't the only time a car ferry had capsized. Just 7 years earlier, in 1987, the Herald of Free Enterprise suffered a similar fate. The ship had just left the port of Zeebrugge in Belgium, carrying 459 passengers and 80 crew.
We arrived by helicopter. We went down in the ship, and it's incredible to see what happened. People were drowning in the ice-cold water. We tried to get them out, but it's a terrible thing.
The Herald was less than 1,300 meters from the harbor entrance, but despite being so close to land, many of those on board didn't stand a chance. The authorities have long since given up any hope that anyone is still alive out here. 193 people died. In this case, the bow doors have been left open, but the results were the same as for the Estonia. Once water was on the car deck, free surface effect took over, causing the ship to capsize. Various solutions to the problem of free surface effect were tried. One of the first were removable bulkheads. These partitions reduce the size of the open spaces on the car deck, limiting how far water can move. But for short journeys, they increase loading time. Another solution, sponsons, are like huge lifebelts for boats, buoyant boxes that fit around the ship to increase stability. But they also increase fuel consumption, and they can make the motion of the ship uncomfortable for passengers. The eventual solution was far more radical and could only be implemented on brand new ships. It required a substantially different basic hull shape. Wider and more box-like under the water, modern car ferries are inherently more stable. The Adventurer was built in 2003. It's one of the most advanced car ferries operating today and employs a wide and box-shaped hull.
The hull shape does make a ship more stable. We are streamlined at the front, but as you come towards the middle, we're very boxy. And just imagine a box in the water, you know? The thinner the box, okay, the more it's going to rock, okay? But the wider the box, the less it will move in the seaway.
As well as having an inherently more stable hull, the Adventurer has been designed with another feature to deal with free surface effect. Drains, or in nautical terms, scuppers. These drains deal with the problem of water on the car deck in the most effective way possible, by getting rid of it.
The important thing is to keep water off that car deck at all costs.
What we have essentially is big drain holes. The water would go down these drain holes into a big holding tank, okay? And the pumps would then be started to pump this water out of this tank. As the water came in, it would be pumped out.
But in the Herald and Estonia disasters, stability was only part of the problem. Bow doors and visors were the other factor. The Estonia used a vertically opening bow visor. These were popular at the time, but had two weaknesses. Firstly, in heavy weather, there's an upward force in the bow visor from the impact of waves, and this imposes a huge strain on the hinges. The second problem was that the bow visor was directly attached to the car loading ramp behind. When the hinges failed on the visor and it fell off, the ramp was pulled down, and this allowed water to immediately enter the car deck. There were no fail-safes.
It was such a shock to everybody, and it was clear that something had to be done. It had to be done very quickly indeed.
Part of the solution to these basic problems was to move away from using bow visors. Most modern car ferries are now constructed using horizontally opening doors. The advantage is that waves hitting the doors push them inward rather than upward, actually making the structure more solid. The second level of protection is to provide a secure watertight bulkhead behind the bow doors. On the Adventurer, this is formed by the car loading ramp. It's entirely separate from the doors, and once raised, is locked in position.
This ramp, when in the fully closed position as it is, forms an integral part of the ship's collision bulkhead. If the outer hull is breached, for example, if we were hit by another ship in the bow area, as long as the bow ramp here integrity is not breached, it should allow no water ingress onto the car deck.
Should anything go wrong with the bow door arrangement, it's vital that the crew know about it. Like the Scandinavian Star, both the Herald and Estonia disasters were made worse by a lack of information.
The Herald and the Estonia didn't even know water was coming into the deck.
The Adventurer and virtually all modern car ferries are fitted with advanced monitoring systems, CCTV, and flooding alarms to alert the crew immediately if water is entering the car deck.
Here we have the water detector alarm. If any water comes onto the car deck, water will flow up into the pipe. There's a sensor inside that detects the water and sets the alarm off both visually and audibly on the hull integrity panel on the bridge, so we can immediately know if there's water on the car decks. Back that up with the visual check on the CCTV.
CCTV system on the ship covers the whole ship, the whole engine room and the whole of the car decks and outside decks. It's very, very beneficial to us in emergencies. If, for example, the bow is breached, you can see straight away down there if there is water.
Systems like this were introduced after the capsize of the Herald. They drastically reduce the chance of a vessel leaving port with its doors open, and also allow the captain to constantly view the status of the bow doors and car deck whilst at sea. Virtually all modern car ferries are built with these improvements, and it's because of what happened to the Herald of Free Enterprise and the Estonia. Thanks to these advances in design, car ferries are now safer than ever before. But ship designers haven't stopped there. There's a radical new type of ship that addresses all of the problems faced by car ferries, the high-speed catamaran.
At the moment, we're travelling from Dún Laoghaire to Holyhead on the Irish Sea. We're travelling at 40 knots on the Stena Explorer, which is the world's largest high-speed catamaran ferry, which is 126 metres long, powered by 4 gas turbines, which are equivalent of aircraft engines.
These 4 engines produce a staggering 100,000 horsepower. They drive 4 of the world's largest water jets, which between them pump out 100 tons of water every second. This gives the Explorer a top speed of 40 knots. It's also hugely stable thanks to the 2 hulls being set 40 metres apart. And because it's so wide, cars can perform a U-turn inside the ship and enter and exit using stern doors. This means it has no bow doors. The Explorer is cutting edge and has every imaginable safety system designed in from the start. But this ship has one safety feature that overrides all the rest. In case of a collision that damages the hulls, it'll stay afloat even when inundated with water.
And wreck the ship, which means taking the bottoms out of both hulls, and the ship will still float. She'll float at the car deck level, which is a very safe position to be in.
The Explorer can do this because she's very light, a result of being designed to operate at high speed. While the Explorer seems to be an ideal solution to the challenges faced by car ferries, there's one problem it faces that's extremely difficult to overcome: fuel consumption. The price for such high speed is reduced fuel economy. As a result, the high-speed catamaran sometimes only operates at reduced speed. There will always be a demand for the unique service that ferries offer, so naval architects keep working to develop the ultimate design. In Norway, there's a radical new ship that one day may provide a solution: the X-Bow. This ultra-modern vessel could be the future, not just for ferries, but all types of ship. Ship design is an evolving process, and naval architects constantly strive to improve safety and efficiency. And the latest advance is the X-Bow.
This is a totally brand new concept that does not exist in comparison anywhere in the world.
This futuristic-looking design is already in use on commercial ships, but may soon be implemented on passenger ships.
The most important aspect is better heavy weather performance. You can actually pass through heavier seas at higher speeds.
There are 2 reasons why the design can do this. Firstly, this type of bow has volume much lower down than a conventional bow. This means as the ship encounters a wave, the increase in buoyancy is gradual and constant rather than sudden and rapid, as on a traditional ship. This makes the vessel's motion smoother. The second reason is that the X-Bow is not flared. Conventional bows curve out at the top. The X-Bow doesn't. This means energy isn't wasted trying to push waves out of the way, so a higher speed can be maintained.
Now what we see here is the traditional offshore bow moving in North Sea heavy conditions at 12 knots. And this is the Ulstein X bow moving in much larger sea states and even higher speeds than compared to this one. And you can clearly see the difference in how they encounter the waves. Now, the normal traditional bow always tries to push the water up and away from itself, whereas the Ulstein X bow tries to go through it in a more smooth way, just deflecting water along its side.
In this footage shot in heavy weather in the North Sea, the difference between the two types of ship is apparent. The traditional bow is lost in a plume of spray as the X-bow almost glides forward. But testing models of the new design wasn't all plain sailing.
So when we first approached the model test facility, they were kind of skeptical to the concept because they believed that the ship would probably go under as soon as it hit a wave. So we found that we wanted to test the boat in a developed high sea state where you encountered a big wave in high speeds. So this boat is now moving along at 14 knots, hitting a wave at approximately 14 meters. And even in this wave, the boat survived well. And that was a very good day, actually.
One of the primary advantages of the design is that it reduces the slamming effect of waves on the bow.
If you see the gray spot here and here on this vessel, those are pressure cells that measure bow impact loads. And we've seen that the Ulstein X bow never have any bow impact loads of significance. Since you don't have that continuous slamming impact, you're not as exposed to structural damage as compared to a traditional type bow.
This is a potential benefit for ferries.
We have a separate design that we are now developing for ourselves, and we know for a fact that loading is going to be significantly less than for a conventional flared bow vessel.
The design has several other assets for passenger shipping. Because it's able to operate regularly in heavier weather, there should be fewer cancelled or delayed sailings. And as the ship is subject to less stress, the manufacturers claim that maintenance costs should be lower. And fuel costs will also be reduced because the design moves more efficiently through waves. Maybe one day, all ships will look like this. Back in Italy, the finishing touches are being added to the much more traditional-looking Ruby Princess. When all the onboard systems have been successfully tested and the ship is handed over, the owners will have a vessel that has been built with knowledge that's been gained over hundreds of years. From safety monitoring systems to watertight compartments, even the most sophisticated aspects of her design can have their heritage traced back to ships that have sailed before.
This process of continual improvement will never stop, nor should it. That's what it's all about.
Although accidents will sometimes still happen, naval architects hope that by learning from the tough lessons of the past, modern ships will sail safely into the future.